Hello everyone, welcome and thank you for joining us today. My name is Heto and I serve as one of the co-presidents of UTMIST this year. It's a pleasure to meet you all. We are the University of Toronto Machine Intelligence Student Team, a fairly lengthy name which we shorten it down as UTMIST. The AGM, or the Annual General Meeting, is one of the largest events that we organize throughout the year to mark the beginning of the academic year and lay out our plans for the months ahead. Our AGM's primary goal is to help you realize that there is a diverse community of like-minded individuals who are passionate as you to learn more about machine learning. This year, we also have the privilege of inviting two notable speakers to help us better understand the landscape of machine learning and dive deeper into how machine learning can help you find meaning in chaos. So without further ado, let's get started. So what can we expect today? We'll first be going over a brief overview of who we are as a club. We'll then share the podium with Professor Roger Gross, who will break the theory of deep learning into manageable chunks and help us understand it. Following that, we would explore the events and projects that we have in mind for the upcoming year and how they could help you take the next step in your machine learning journey. We'll then be joined by Sheldon, who is one of our founding members of UTMIST and currently a PhD student at the University of Toronto. His talk with Professor Rogers is one of the most awaited sections of our meeting today. Once you have immersed yourself in these talks and found the motivation you need, we'll then move on to introduce our executive team and discuss about how you can join the club. This will be followed by a Q&A session to help resolve any questions that you might have. So who are we? We are a student organization devoted to promoting a vibrant machine learning community on campus and connecting students with graduate students, professors, and industry experts in the field of machine intelligence to clear the mist around machine intelligence for the eager young minds. Founded in 2017, we ran a series of successful initiatives, including MIST 101, which is an introductory workshop series, the Discover AI Challenge, which is a hackathon organized with collaboration with Microsoft, the guest speaker series, technical workshops, paper reproduction teams, applied machine learning projects, and a lot more. Our team now consists of several graduate and undergraduate students and reaches a community of 950 plus registered members. Continuing this legacy, we aim to take on additional challenges to continue to provide students with more resources and opportunities. We are collaborating with research institutes and industrial companies to present more paper reading sessions and technical workshops, while also facilitating student groups to work on applied and research projects on machine learning. Our ultimate goal is to build a platform to increase industry engagement, connecting students who are passionate about machine learning with research labs and industrial companies that are actively looking for bright minds to join them. We are striving to close the aforementioned gap between workforce and student communities. With a community of more than 950 registered members, we have developed a huge knowledge base for our audience that can act as an excellent resource. We have a Discord server dedicated for all people interested in machine learning. Our members help resolve the questions that you might have via our Discord help channels. For beginners in machine learning who are short on experience but have a great passion to learn, we have the study groups and the paper reading groups to help you advance further in your career. These are just a sneak peek into the whole pool of opportunities that UTMIST brings to you. They will be discussed in more detail as we progress further. Now we'll pass on the stage to Professor Roger Gross, who is an assistant professor at the CS department at U of T. He is also the founding member of the Vector Institute. His research focuses on machine learning, especially deep learning and Bayesian modeling that aim to automate the configuration of machine learning systems while taking AI ethics into account. It's a pleasure to have you with us, Professor Gross. Now on to you. Vicky, you can stop sharing the screen so that Professor can share it.
Thank you, Hitav. I'm Roger Gross, and I'll be talking about deep learning, what it is, and why it's been so impactful. So I'll spend about 30 minutes giving an overview of deep learning, and that'll be followed by open discussion. But also, please, you're encouraged to ask questions throughout. You don't have to hold your questions till the end. So deep learning is an area where Canada and the University of Toronto in particular pretty much changed the way that computing is done. So here's an image of the 3 Turing Award winners from 2019. They collectively received the Turing Award for the discovery of deep learning. The Turing Award is essentially the computer science equivalent of the Nobel Prize. And so these 3 individuals are University of Toronto professor Jeff Hinton, University of Montreal professor Joshua Bengio, and Jan LeCun, who currently directs the Facebook AI research and had also spent a lot of time at Toronto. And so before I say what deep learning is, first of all, what is machine learning? Well, for a lot of problems we might be interested in implementing a computer program for, it's really hard to program the correct behavior by hand. So if you think about how we do all the things we depend on a day-to-day basis, like how do we recognize faces, how do we understand speech, we really have no introspective awareness of it. We can't break it down into small chunks that we can write in Python. And so the machine learning approach says, rather than programming behaviors directly, let's instead program an algorithm to automatically learn from experience or from data. And there are a number of different reasons for doing something using machine learning. So one of them is that it might just be really hard to implement the solution by hand, right? But another reason is that we might need the algorithm to adapt to a changing environment. The classic example being spam filtering, right? So we all depend on services like Gmail being able to filter out spam emails. But this is a problem where directly programming it would be very hard because the spammers will be able to play around with the system and figure out ways to beat it. And so the spammers are constantly improving. And so the system will have to adapt to the changing environment. We also might want the computers to perform better than the human programmers. If you want to program a chess agent by hand, you might be limited by the sorts of heuristics you can come up with as from introspection, and so you won't be able to write a program that plays better than yourself. Right? So if you want the program to play better, then it should have some sort of learning element to it. And finally, there are ethical considerations, in particular privacy and fairness. So if you were to write a spam filter and you wanted to write the rules by hand, this might require you to sit there scrutinizing lots of people's emails. That's something we don't want, right? With an automated algorithm, it can learn automatically from real emails without a person having to look at them. And similarly, if humans are writing all of the individual rules, then we have to worry about fairness issues. What biases are we contributing? Learning from data doesn't guarantee that we can eliminate all the biases, but at least it gives us some chance of doing it in a reasonably fair way. So what about deep learning? So deep learning is the study of deep neural networks, and neural networks at some level were inspired by the brain. The brain is a really complicated thing. Individual neurons carry out complicated operations. They receive a lot of chemical signals at their synapses. They convert them to electrical signals and integrate them. If the electrical signals exceed some threshold, then the neuron will fire. It'll send an action potential down its axon to other neurons, and so on. And so the biology is pretty complicated. But when we build neural networks as computer scientists, we're using a vastly oversimplified model of neurons. So in particular, we can represent neurons in terms, so we draw them diagrammatically. We represent them with these circles. Each one represents a neuron-like unit. They receive connections from other units, and we represent the strengths of these connections with weights, Wi. You can think of these weights as like the strength of a synapse. And so these units carry out a fairly simple arithmetic operation. What they do is they integrate the incoming information from their inputs. So we have the network compute a linear function of the input signals they receive. And this is a notation from linear algebra. It represents a dot product. You could also write this out explicitly as a summation over the indices of wj times xj. So they multiply each of the input signals by the corresponding weight, and they sum the result. Then they add to it a bias parameter, which says how much this neuron likes to activate in the absence of any incoming signal. So they take this entire sum, and then they pass it through a nonlinear activation function denoted with the Greek letter phi. This activation function could, for instance, clip the values to be positive. And so all that neural networks are just collections of thousands or millions of these really simple processing units that in combination perform useful computations. So you'll see all sorts of really fancy neural net architectures involving layers connected in various ways, but all they are is really just large connections of these extremely simple processing units. And so perhaps the first machine learning algorithm was the Perceptron algorithm, which you can think of as a single one of these neuron-like units. And it was a particular rule for learning the weights for that unit from data. So here it is implemented on punch cards. And so the perceptron was a neuron-like unit with a hard threshold. And we can think about it as applying a linear decision boundary. So what that means is that if we, for simplicity, imagine we have two input signals represented as x1 and x2. And so we can draw what's called input space corresponding to all possible values of the input signals. And the neuron will essentially define a half space. So in 2 dimensions, a half space is just one side of a line. And everything on one side will be classified as positive, so the neuron will output 1. The other side will be classified as negative, so the neuron will output 0. And the perceptron is capable of computing simple logical functions like and, or, and not. So this is a representation of and. So if both of the inputs are 1, then the neuron should output 1. But if either of the inputs is 0, then it should output 0. And so this function can be represented with a linear decision boundary. These are the weights and biases that correspond to the function shown here. Unfortunately, there are some things that perceptrons cannot compute. And in particular, can't be computed by a linear classifier. The classic example is exclusive OR XOR. So this is the function that we would like it to compute. And you can probably see by inspection that there's no way you can draw a linear decision boundary that will separate these two classes. So people got very discouraged about neural networks for about 2 decades, because like you could only represent very simple linear functions. But by adding another layer, you can compute things like XOR. And so you can sort of think about this like designing a circuit. Right? If you were to build a Boolean circuit to compute XOR, you might have an AND gate and an OR gate, and then sort of combine the outputs of those. So essentially, we can define a 2-layer neural net architecture where the first layer has 2 units. The first one computes OR, that can be computed with a linear function. The second one computes AND, that can also be computed with a linear function. And then the output unit will basically check that the OR unit is on and the AND unit is off. And so these particular weights compute that function, and this is what the result looks like. It successfully computes XOR. And so you can ask, are there functions that can't even be computed by deep neural networks? The answer is no. So deep neural networks, or even 2-layer neural networks, are universal. And by universal, I mean that any given function can be approximated arbitrarily accurately by a neural network. This is probably easiest to think about in the binary case. So if we assume that the inputs and the targets are all binary, then the way we can design a network is by writing out a table where each row of the table corresponds to a possible input configuration. And then we specify the value we'd like the network to output in that case. So we can design a network with 2 to the d hidden units, where each of the hidden units responds only to one particular input configuration, one particular row in the table, and then we can design the weights in the output layer based on what we would like the network to output. So this gives a recipe to construct a neural net to compute any particular function. Now, this isn't a particularly useful result because on one hand, this network has to be exponentially large. So it's essentially just memorizing the data. It's not capturing any useful patterns. And the other reason it's not so useful is that this doesn't tell us anything about how to actually learn the function, right? It could be that arbitrary functions can be represented by neural nets, but it's just like impractical to find them. And so the algorithm that made this all possible was the backpropagation algorithm. So I mentioned earlier a Perceptron algorithm, but that only works for individual, for running a single unit. It's not straightforward to extend to an entire network. And so the idea is rather than apply the perceptron learning rule, we're going to try to do gradient descent on the weights of the network. So the way to think about this is that we define a cost function j, which says how unhappy are we if the correct answer is one thing and the network predicts another thing. So we define this cost function, and we compute the partial derivatives of it with respect to each of the weights of the network. That essentially says, if we perturb this weight by just a little bit, how much will the cost change? Which direction will it change in? And then we update the weight based on the gradient direction. So if the partial derivative is positive, that means that increasing this weight will increase the cost, which means we would like to decrease it. Correspondingly, If the weight is negative, that means that increasing the weight will reduce the cost, therefore we'd like to increase it. So the gradient descent rule updates each of the weights minus scale factor alpha times the partial derivative with respect to that weight. This alpha is called the learning rate that essentially determines how large are the steps that the algorithm takes. And so it's not immediately obvious how you would compute all these partial derivatives efficiently. And a naive implementation would just be impractically expensive. So the key invention was the backpropagation algorithm, which basically just gives an efficient way to compute all of the partial derivatives with respect to the weights of the network. So this algorithm was invented by U of T professor Geoffrey Hinton and colleagues back in 1988. And this is the algorithm that's used to train pretty much all of the neural networks that are in use today. So when we talk about deep learning, we're basically referring to neural nets with many layers. And so here is a classic architecture that was invented by University of Toronto grad student Alex Krzyzewski back in 2012. This is the AlexNet architecture, which recognizes objects and images. And this is considered the thing that basically kicked off the whole deep learning revolution. It got companies to make big investments in deep learning research teams. It got the academic field excited about doing more deep learning. Basically, smashed all of the object recognition benchmarks that people have been working on at the time. And so this network consists of a series of layers. Each layer is basically just a collection of units, similar to the ones we saw a few slides ago. So this layer represents the input image. And then this layer consists of a large number of neurons, which each look at a small patch of the input image, an 11 by 11 patch. They compute the same sorts of linear functions as any other unit. And then the next layer looks at the units from the previous layer, and so on. So it's the same sort of neural net architecture people have been using for decades, but much larger and deeper. And the promise of deep networks is that we can learn units that respond to high-level abstract features. And so here's a visualization of what each of the units in an AlexNet-like architecture are doing. These are units from the first layer of the network. And what this represents essentially is they try to find an image that maximally activates the units in a layer. And so if you want to maximally activate the units in the lower layers of the network, you get essentially these simple textures. They maybe correspond to a particular frequency and orientation. As you move up to the network, you start to see kind of higher level and more abstract textures. Right? This one maybe looks like a pattern of flowers or something like that. And then as you get close to the top of the network, you start seeing things like control panels and human legs, faces of dogs, and so on. So each layer is able to compute progressively more abstract and higher level features than the layer before. Just going to check the chat to see if there are any questions. Okay, not yet. All right, so that's the idea behind deep learning. And why has it had such an impact? Well, it started with the work of U of T grad student Alex Krzyzewski. His AlexNet architecture learned to recognize objects and images far better than competing approaches, just completely demolished the benchmarks that people have been working on in the field of computer vision. And now deep learning has become the core technology in essentially every subfield of AI, except so far automated reasoning. Someone asked in the chat, did ConvNet arrive before AlexNet? Yes, they did. Actually, this gets to my next point. Right, what was so different about AlexNet? Well, modern deep learning is enabled by specialized hardware, in particular, two kinds of technologies, graphics processing units. As the name suggests, these were originally developed for graphics, but what they really are is a kind of hardware that's really good at doing highly stereotyped computations in parallel. So if you have code that requires doing exactly the same thing to different parts of the data and doesn't require a lot of control flow, that would be a good candidate for implementing on a GPU. And so it turned out that GPUs were really good at doing matrix multiplication. And matrix multiplication is the single operation that makes up the vast majority of the work in deep learning. But GPUs weren't really specifically designed for matrix multiplication. It's just something that they turned out to be good at. And so once deep learning became popular, they designed tensor processing units, or TPUs, which were just special purpose hardware designed to be insanely good at doing matrix multiplication. And so if you can implement your neural net on a GPU, it can run maybe 100 times faster than what it would on a CPU. And then TPUs, I don't have the exact figures, but they give a similar kind of speed up. So in addition to specialized hardware, the other thing that happened over the past decade is the creation of neural net frameworks that not only have implementations of the sorts of operations that we need for neural nets, but they also provide important functionality like automatic differentiation. So I talked about the backprop algorithm earlier and how it's so important to compute the partial derivatives with respect to the weights of the network. Well, now we have these tools called automatic differentiation that basically compute all the derivatives for you without you having to think about it. So 10 years ago, you would have had to implement a machine learning algorithm by doing lots of mathematical derivations that could be error prone. But now you just feed it into an autodiff routine and you don't have to think about it. They provide libraries of algorithms and neural net primitives. They provide easy support for GPUs and TPUs, so that if you want to change from CPU to GPU code, you can just set a flag in your configuration file rather than having to write all this arcane CUDA code. So the field of machine learning has been rapidly expanding. So NeurIPS is one of the two main conferences of the field. And there's been an exponential growth. It's been doubling pretty much every other year, almost like Moore's Law or something like that. And it became so popular that in 2018, the conference actually sold out in the first 12 minutes that the registration was available. And so getting back to this question about what was so different about AlexNet compared to past ConvNets. So the first ConvNet was invented in 1988, I believe. And then the first really successful one, Linnet, came about a decade later. That was the one that was able to recognize handwritten digits accurately enough for the US Postal Service to use it for automatically recognizing zip codes and envelopes. And AlexNet was in 2012, so I guess about 25 years after the original Convet. And it was essentially the same architecture, right? So all of the individual layers, the sorts of operations it did, were pretty similar to the ones that were created in the 80s and 90s. So the thing that was actually different was that we had much better hardware. And so it turns out that deep learning just is able to easily take advantage of more compute power and more data. And one of the surprises is that the scaling as a function of resources is just incredibly regular. So there was a model called GPT-3 for modeling the distribution of English text that was released a couple of years ago. And one of the striking things about this work was that they actually measured the performance as a function of data and the size of the network and things like that. And so there's a particular metric they use, shown here on a log scale on the y-axis. And here on the x-axis, they're showing the size of the network in terms of the number of parameters. And over 5 orders of magnitude, we get a perfect power law fit, and how the performance depends on the size of the model. Similarly, if you measure how the performance depends on the size of the data set, it's a perfect power law fit. And so, unlike the learning algorithms that came before, neural nets are able to automatically take advantage of more data and more compute resources, which is why, or at least one of the big reasons that they've been so successful. And the fact that the scaling is so regular means that companies have been willing to make huge investments in training neural net algorithms. So this GPT-3 system actually was estimated to cost more than $1 million to train. A major success story of neural networks has been generative models, which try to produce samples from a distribution of natural images or English text or some other data domain. And this saw very rapid progress over a short period of time. So back in 2016, these were the highest quality images that could be generated from the model. It's obviously captured some of the structure of images, but it hasn't really gotten it right. But then 2 years later, you could actually get pretty high quality images, and the quality has actually just improved since then. Another big milestone for deep learning came in the area of game playing. So game playing was traditionally one of the big ways of measuring AI progress. Back in the 1990s, there was a big milestone when IBM's system Deep Blue defeated the world chess champion Garry Kasparov. But the way that Deep Blue worked was essentially using a massive compute cluster to do a huge brute force search over the game tree. And it was all about searching as deeply as possible, but only use machine learning in a very kind of simple way to weight a few hand-designed features at the bottom level of the tree. So after AIs defeated humans at chess, the last game standing was Go. And Go was something that no one really knew how to solve using those sorts of techniques because it relied so heavily on pattern recognition and couldn't be done using brute force search because the tree was just too large. But finally, in 2016, a system called Alphago, which was built by DeepMind, and in particular was the internship project of U of T grad student Chris Madison, now a U of T professor, So AlphaGo defeated the human Go champion Lee Sedol. But what was interesting was that it didn't do it using brute force search. It actually used deep learning. So it was much more heavily based on pattern recognition of the sort that's much more similar to how humans might play the game. And in fact, a lot of the moves seem to be strikingly human-like. So I mentioned this GPT-3 language model. What's a language model? Well, the language model is just trying to model the distribution of natural language texts. And what it's trying to do is, given a sequence of words, predict the distribution over the next word. Right? So maybe it has like, it assigns a 20% chance the next word is the, and so on. And so once you've trained this model, you can generate English text just by sampling from the distribution. So people have been working on language models for a long time, but it was not until a couple of years ago that they actually became really good at generating English text. So here is an example of text completion by GPT-3. So we give it the following prompt: McSweeney's internet tendency, daily humor almost every day since 1998. Back yet from another globetrotting adventure, Indiana Jones checks his mail and discovers that his bid for tenure has been denied. Okay, dear Dr. Jones. All right, so that's the prompt that GPT-3 was given. And here is the output that it produces. So this is what it thinks is a sample from the distribution of English text conditioned on the prompt that it was given. And this really reflects an impressive amount of knowledge. It has to understand what's the style of a rejection letter, right? I am sorry to inform you. And then it starts with a bunch of praise before going to the criticism. It has to know some facts about pop culture, right? It's not told in the prompt that Indiana Jones is an archaeologist. It has to know that. It knows something about what sorts of adventures Indiana Jones is likely to get into, and so on. So you can see a lot more examples of GPT-3 at this website shown at the bottom. And there are also various websites where you can interact with it in some form. All right, so I'll open it up to a general discussion. Okay, so someone asks, but doesn't actually understand language, right? So it's hard to tell. So the word understand is fairly loaded, and you can get into philosophical arguments about, there's the classic Chinese room argument. If you have a machine that has a big lookup table that allows it to answer questions in Chinese, does it actually understand Chinese, and so on. But I think GPT-3 is at the point where if it's actually able to answer some of the questions that it does, so people have given it physics interview questions that it answered, gave them reasonable answers to. And it's at the point where if you claim that it doesn't understand anything of language, you'd probably have to, you could make some predictions about the outcomes of experiments that we could run in the next couple of years, right? So it might turn out that it only appears to be able to answer those questions because it saw very similar training examples. Right? If it was trained on a large section of the internet, it could be that someone else happened to ask exactly the same question and give the answer, right? But I think we're at the point where it's ambiguous. Someone asked, what are the most promising new architectures and what should we expect to see in the next few years? Also, should we expect the road to AGI to be paved by large transformer networks such as GPT-3, BERT, and the rumored 100 trillion parameter GPT-4? Yeah, great question. So I forgot to mention, transformer is also an architecture that University of Toronto contributed to. So GPT-3 was an example of an architecture called transformers. And one of the main authors on the transformers paper was Aidan Gomez, who at the time was a U of T undergrad doing an internship at Google. So, so transformers have been one of the big advances in deep learning in the last few years. And what's special about them is that they are based on something called self-attention, which means that in addition to the computations done by the unit I showed earlier in this talk, they also have an attention mechanism that decides online which other units they should connect to. And this allows it to, if it's trying to predict the next word in the sentence, it can figure out which of the previous words in the sentence or in the context window it should be paying attention to for that prediction. And I think it still remains to be seen how broadly capable of reasoning these architectures are. So, I mean, one hypothesis would be that these are essentially Turing complete, that you don't really need to add anything else. Transformers will be able to do whatever they have to do to solve some problem. It could be that there's some big idea that we're still missing, so it's hard to predict. Okay, someone says, I once saw a quote, most animal behavior is not the result of clever learning algorithms, supervised or unsupervised, but is encoded in the genome. So is there any research direction in deep learning aiming to mimic the genomic encoding in brains for specific tasks? So yeah, it's a good question. So deep learning doesn't necessarily map onto learning during the lifetime of the human or an animal. Right? A lot of the abilities we're applying deep learning to are things that are potentially encoded in the genome to some extent. So vision, for instance, is a capability that most kinds of animals reliably learn, and some already have to a large extent from birth. So the fact that something could be encoded in the genome doesn't really mean that deep learning architectures can't learn it. Let's see, how does computational modeling of language help improve our understanding of psycholinguistics and human intelligence in general? Yeah, definitely. So there's a series of work from Jim DiCarlo's group at MIT comparing the predictions of deep neural networks to human and primate vision, and comparing the representations of individual units to what you'd find in primate brains. And for a while, as the neural nets got better, the representations became more and more similar to those of the brain. And then the trend eventually stopped. I believe, as of a few years ago, that the most modern architecture for object recognition is actually less similar to biological brains than the previous one. So I think there's sort of a lot that could be learned about neuroscience from these models. I'm less familiar with what's happened on the linguistics side, but I think it's definitely, I wouldn't be surprised if a lot of interesting things have been learned from that. Right, so someone asks, can we combine Bayesian modeling with deep learning? So it's a great question. And Bayesian neural networks have existed for a long time. In fact, Bayesian networks were one of the original Bayesian learning algorithms considered in machine learning. They were pioneered by U of T professor Radford Neal back in the 90s. And in the early 2000s, Bayesian neural nets were among the best approaches for supervised regression with small amounts of data. And you might have expected when deep learning really took off that Bayesian neural nets would sort of rapidly improve along with everything else. And I mean, to some extent, we have them. They work in some ways, but they haven't really met all of the things we'd hope to get from Bayesian modeling. There's certain capabilities that Bayesian methods have, like preventing a model from overfitting and things like that. But there are a lot of other ways to achieve. You don't necessarily need Bayesian models. There are other things that we might hope to get from Bayesian modeling, like being able to select between a set of candidate models that have very different structures. And this is something that we don't really have working yet in Bayesian deep learning. And it seems like the requirements for the accuracy of inference in Bayesian neural nets to be able to get these sorts of benefits are still beyond what we can do in a scalable way today. So I think there's still promise for it, but it hasn't really taken off yet.
Thank you everyone for the questions. Right now we only have time for one more question, and we'll need to move on to the next sessions of the AGM.
Yeah, so someone asked if we've looked at models applying attention to the training data distribution. So it's a great question. I think there are some algorithms that sort of get at this. There's a class of algorithms called Gaussian processes. These aren't actually neural nets, although they can be seen as the limit as Bayesian neural nets get infinitely large. And the way that Gaussian processes make predictions can be seen as a sort of attention mechanism. So the prediction at any particular point can be viewed as maybe a weighted average of the values at nearby training points. So there have been various papers recently that try to understand neural networks in terms of Gaussian processes that they approximate. So most notably the neural tangent kernel line of work. And so this gives an interesting interpretation to what neural nets are doing. It's something that's fairly hard to do at scale. So I think it would be very interesting if we were able to take the GPT-3 outputs that were so surprising. So if we took the Indiana Jones story, could we look at the training set and figure out which of the training examples contribute to that particular output? That might give us an example, or give us some insight into what level of abstraction it's thinking at when it does that. And we have, conceptually, we have algorithms that are able to answer this question at a relatively small scale. We don't have the capability to scale them up anywhere near the level of GPT-3. So it's still an important area of algorithmic research. Right.
Thank you, Professor, for the amazing talk on deep learning and why it has so many impacts. We really appreciate it. Now we'll move on to the next sections of the AGM. So let me share my screen again. All right, next we'll talk about some of the initiatives we have for the 2021 school year. A big part of UTMIST is facilitated machine learning projects. Every year we take on a few interesting ideas, either applying ML to solve complicated real-world problems or chasing deep cutting-edge research in ML. One example of our real-world applications of ML concept is this year's project called ECG analysis using deep CNN, where our developers will investigate a convolutional neural network model proposed by a group of biomedical researchers, in which it's used to classify the health state of hearts and specify cardiovascular diseases by analyzing the ECG diagrams. We also have many research groups affiliated with UTMIST that have published their own academic paper while in their undergrad years, work on different departments and professors to develop cutting-edge research and prototype technology. Another example is the stock price prediction project. The team would like to create an AI that is practically useful, which means it can make money. They will try a variety of ML algorithms from simple RNN to NLP, and maybe reinforcement learning. And at the end, the work will be deployed as a bot to trade with paper money. Want to find out if the bot can actually make money? Apply now and become a project developers. These research teams at UTMIST are supported with ample resources, connections, and guidance as they progress with their project throughout the year. We also organize events and talks frequently where we invite distinguished researchers and industry experts to share the latest breakthrough and applications related to machine learning. Many of them are also sharing opportunities for you to join their team as an intern. We also have our own newsletter covering the latest conference paper and industry news to thousands of readers. There's a QR code on the bottom left of the page. Scan it and make sure to sign up for our newsletter. Okay. For this school year, we're planning to collaborate with other student organizations to host 2 hackathons. The first one is the Climate Hack. It will be a 1 to 3 months long event starting from November to February. As of now, 12 universities have signed up, including MIT, Caltech, Oxford, etc. The first phase of the hackathon will be online, and the finalists of each university will then move on to the second phase. We're planning to have the second phase of the hackathon in London, UK next year. The second hackathon is a collaboration between the Rodman and engineering community. This hackathon, we plan to give students another medium through which they can demonstrate entrepreneurship and apply professional skills practically. We will reveal more events throughout the year, so remember to join our Discord server to stay updated. So that's a brief overview of our plan for next year. Next, I would like to introduce Sheldon, our speaker for the next talk. Sheldon Huang is currently a second-year CS PhD student at U of T and the Vector Institute, advised by Professor Roger Gross. His research interest lies in deep learning and AI safety. He's generally interested in statistics, information theory, psychology, philosophy, and more generally, intelligence at all levels of abstractions. He was the founding president of UTMIST in 2017 and remained involved as an advisor ever since. Let's welcome Sheldon.
Thanks for the introduction. Let me share my screen 1 second. Can you guys hear me?
Yep, we can hear you.
Okay, it says host disabled participant screen sharing. Can you grant me the access?
Sure.
Okay, thanks. Try again. Oh, it works now. Okay. All right, can you guys see my screen?
Yeah, we can see your screen.
All right, okay, yeah. Okay, hello everyone. Hope you're enjoying the AGM so far. And up until this point, we're trying to introduce you to machine learning and UTMIST. And hopefully after Roger's talk, you are now excited about deep learning and have some rough ideas of what it is and its significance and meaning to the world. I want to give another perspective on why deep learning, the perspective from the self. This talk will be all about you. I want to share some strategies and thoughts on how deep learning could help you find out more about yourself. And it's basically a research project on the self, so that's why I call it me-search. The main motivation for this talk is that I got asked a lot of questions from my mentees in U of T mentorship programs and from U of T people. And then I started to notice some patterns because they share a lot of similar elements, such as how to find the right courses, programs, career path, and so on. So I thought, there's this one question to answer them all, actually. And this one, basically this question is, who are you really? And this one big question also follows nicely from my talk at last year's EGM. So when asked to give a talk, some of the observations and thoughts on this topic, tailored to people who are considering exploring machine learning as a career. By the way, if my internet goes off at any time, please let me know. I'll try to fix it because my internet is a little bit unstable today. Okay, so I will start with summarizing last year's talk in just one slide. And here you go. So last year's talk started with my observation that we live in an age of short-lived hypes. The crowd constantly switch from one hype to another. And not that it's absolutely a bad thing, but without ever diving into a field deep enough to see the wonderful worlds that are hard to reach, you would be missing out a lot in life, maybe including a fulfilling career too. So how do we find the hype that lasts? To summarize last year's talk in just one sentence, long-lasting hype starts with the curiosity, but stay with meaning. So curiosity plus meaning gives you the long-lasting hype. That talk was a long story and lots of content, lots of memes too. Well, the pandemic was hitting everyone hard last year, so I thought everyone could do with some happy memes like this one. to save time, I won't get into any more details here. If you're interested, you can watch last year's talk from scanning the QR code. So this year, well, last year we kind of left at how to find meaning. I didn't get too much into like exactly how to find meaning, and this year I will follow up on that. Meaning is such a big topic and is as old as basically the human civilization. So let's start with scoping it down a little bit by asking ourselves, how to find meaning in university? As I think most of you are in university. So when I was in my first year engineering science, I was living basically 50% at Chestnut and 50% at this all-you-can-eat cafeteria. So near the end of my first year, I realized that university is itself essentially an all-you-can-eat cafeteria. You come here empty-stomached, eager young minds with potential and capacity at your disposal, now immersed in a sea of infinite knowledge, resources, and possibilities. Whether you know it or not, with every passing moment, you're spending that potential to buy whatever you are paying attention to, whatever you are getting in the cafeteria. So we should seize our day. Every day we wake up, we receive the gift of another 24 hours, and one day it will be our last 24 hours. So this somehow reminded me of this old movie I watched in high school called The Dead Poets Society. And then I had an epiphany. So in an all-you-can-eat environment, it's never about who can eat the most. We're merely mortal beings with a limited-sized stomach. So it's all about what you eat. This is the meaning of an all-you-can-eat environment. It is an opportunity for you to understand your taste buds better so that when you get out of it, you know exactly what you're after at your next stop. So you know where to look, where you can find the meaning of your life. So by the way, so after that, I moved out of Chestnut and I dropped out of Einstein, and then the idea and name of UTMIST was conceived, and I audited Roger's ML course and started my ML journey with Roger and learning from him ever since. But it feels very interesting to be talking about this at UTMIST after 5 years. I feel extremely grateful for my environment, especially the people around. So, okay, before we get into exactly how to figure out what to eat, let's first appreciate its full difficulty and the nature of this problem. So first of all, we don't just know ourselves automatically. It requires conscious effort. It's just like how you don't really know anyone automatically. You get to know them through communication and interpretation. And only then a mental model of them start forming in your head. And it is a common saying in statistics that all models are wrong, but some are useful, or like neural networks. Well, all models are wrong because we can never know the true model. We can only approximate them through prior knowledge and data. This fact will become very clear when you dive deeper into machine learning, and I think the same applies to human. And this includes yourself. That is your mental model of yourself. Furthermore, some people spend much more time thinking and interacting with other people rather than with themselves. And the results is that they could have a more accurate mental model of others than of themselves. It just directly follows, right? But isn't it a scary thought that you'll never have the ground truth of anyone, including yourself? The best you can hope for is an accurate, approximate mental model. And when some people realize that they actually don't really know what they want, they do get scared and think it's a bad thing. But I think it has a lot to do with the social media nowadays, where people are trying to show off their achievements as they, as if they know exactly what they want and they're getting it. Or maybe they are, and that deserve congratulations. But it's also possible that only precisely because they don't know what they want and who they are, they need external confirmation so badly that they spend so much effort putting on a show rather than getting rid of all the distractions and lead a truly meaningful life. So under this culture, we're conditioned to feel ashamed of not knowing what we want. And we lie to ourselves and others that we do, and we're doing great. Self-knowledge is perhaps the hardest subject of study already, and this willful blindness and avoidance is just turning hard into impossible. As Jordan Peterson said in his books and psychology courses, this is turning suffering into a bottomless hell. So I'll articulate this point later with some graphical illustrations. But now I just want to say there's absolutely no shame in not knowing what you want. And if someone asks you why you don't know what you want, well, it's kind of like asking, why don't you have $1 billion? Well, you'd answer, well, money doesn't grow on trees. Similarly, we can't assume we are born to know who we are and what we want. It requires conscious effort. Furthermore, imagine in a counterfactual world, like a parallel universe where everyone is just born to know that who they are and exactly what they want. It's kind of like the premise in the book Brave New World. Well, not to mention what a dystopia that would be. Well, I'd rather hypothesize that fundamentally in that world, true art wouldn't even exist, or at least some core components of art would be missing because they wouldn't even have been discovered in the first place. If you want some examples of what I mean, this QR code will take you to a playlist of some classical music, which I think was the composer's way of representing their process of self-discovery from not knowing to knowing. Classical music is my favorite, but I think you can find similar examples in every genre of art. Because this is such a huge part of art, the meaning of art, arguably, art is a powerful language to represent feelings that cannot be articulated easily. There is great power in naming and articulating things and feelings, and I'll come back to that point later, again with graphical illustrations. The human psyche is complicated, and there are things that just cannot be easily named and articulated by logical reasoning nor language. So art might even be the only way for some creative mind to fully unlock its nuance, sophistication because of its representational power. So instead of feeling sorry for yourselves for not knowing what we want, we should feel grateful that we live in a world where this is the default state and there is infinite possibility for discovery to create self-knowledge, and thus we get to live in the world of art. So what exactly is this process of self-discovery? Well, it's essentially a lifelong research project on the self. So research would be an accurate name for it. It's like we're searching for our true self in an inner maze. I believe there's such a maze in every one of us. On the right, so here is the textbook we use for Psychology 260, Learning and Plasticity. It's a course about behaviorism. And it's interesting because the textbook cover means, what the textbook cover means. I think it's suggesting that we're trying to gain further understanding of ourselves through behaviorism. I didn't really think of that when I was taking the course, but later I realized that. So research is a term I first heard from a psychologist. He said actually many of his colleagues chose psychology as their career focus because they have a strong need to understand themselves and figure out life. It's kind of like what the textbook cover suggests. That was an inspiration to me and led me to further understanding of the relationship of work and the self. Essentially, work is satisfying the need of the self. This is why I said in the beginning that who are you really is the one big question to answer them all. Psychology is clearly one way to research, but I think there are other ways too. And in fact, depending on who you are, you might find different strategies to be a better fit. So let's look at some example research stories to get some inspirations and further understanding of research. And then I will present you with a systematic and model-based method. So if you look for research in the stories, you'll start to notice that it's actually everywhere. It seems to be a core component of any good story. Isn't that interesting? I watched and read a lot of fictions in high school, and I just thought they're like fun. But later I realized that the reason why I thought they're fun is precisely because they are showing me examples of research through imagined worlds. I used to think human imagination just comes from nowhere. But in 2019, when I tried to mechanize it with algorithms, like to code them up, I realized that, well, it's actually no. Imagination is from our daily observations. For example, in all the fictions, aliens look either like human or animals or daily objects like cars. So great fictions, like all great stories, are about symbols and archetypes of human nature. They're about what makes us human. And we kind of draw inspirations from those fictions to imagine possible versions of ourselves. So Jordan Peterson articulated this idea in both of his psychology courses at U of T. the personality and its transformation course, and the maps of meaning course. Those stories are fictions, but they can be more real than what we perceive every day. Fictional premises are only tools for empowerment to help authors articulate feelings and thoughts that would otherwise be too sophisticated to be represented clearly. It seems like there's a bunch of random stuff in fictions, but good fictions can actually improve the signal-to-noise ratio, very much like arts, like the random stuff, they're all there for a reason. It's fake, but it's more real than what we perceive often. And here are some examples of such fictions of research. I just listed some examples of different styles on top of my head. But this list is essentially infinitely large because a story wouldn't become classic if it's not about research. And particularly, there's a particular story that I like to mention because it introduced some of the interesting ideas while we explored how to mechanize research in machines, basically reproduce research in machines. So back in 2017, the inspiration I got from this story is that if we can have an algorithm for research, isn't that the promise that human can do it too by just following that algorithm? So yeah, if you have watched Westworld, basically it's a story of how to code up consciousness in robots. And when I was watching the show, that was actually exactly when I started my ML career. It was part of my attempt at research. The first season was Westworld, was actually all about research. The robots in the show are awakening and becoming more human than real human through their research. So quick disclaimer, I have no comment for other seasons. So can we pretend that there are other separate stories and we're just talking about the first season here? So the first season, though, is pretty good. It explored the concept of the bicameral mind. It argues that the evolutionary history of the mind has a stage where the mind was divided by two parts. One part that does the speaking and the second part which does the listening and executing. So in the Westworld story, they try to basically reproduce this in machines and they think that it's the next step of evolution. So the bicameral mind is rather a controversial hypothesis, and I'm not going to get into more details here. If you want more details, you can check out the book called The Origin of Consciousness in the Breakdown of the Bicameral Mind, which coined this term in 1976. So Roger recommended this book to me too, so if you wanna check it out. But I do think there's some truth in this idea, even though it's controversial. This story is essentially trying to imagine an algorithm for research, and it was symbolized by the maze. The maze is the key for the self to unlock its self-awareness. It is a process of true thinking and feeling. It is a very deep conversation with the self, and it is highly non-trivial. So Jordan Peterson mentioned in his book that true thinking is rare, just like true listening. Thinking is listening to yourself. It's difficult. To think, you have to be at least two people at the same time. Then you have to let those people disagree. Thinking is an internal dialogue between two or more different views of the world. True thinking is complex and demanding. It requires you to be articulate speaker and careful, judicious listener at the same time. It involves conflict, so you have to tolerate conflict. And it's hard because you also need a very strong opponent, to challenge your ideas. You can't just, justify your proofs with conclusion so that you don't need to face the conflict and you don't need to change your mind. I think this is exactly what distinguishes intellectually lazy people and intellectually conscientious people. And also Carl Jung said, until you make the unconscious conscious, it will control your life and you will call it fate. Recall earlier I said that self-knowledge doesn't come free and it requires a lot of conscious effort, pun intended. But how to make the conscious unconscious? Right? It's kind of like this iceberg. Most of it is hidden under the water, and basically we need to discover them. So I'll get back to that later, the expert part. But before that, let me introduce a concrete systematic and model-based framework for research that I came up with and have been personally using, so that we can have some context when we talk about that very abstract, unconscious stuff. It contains a model and algorithm, and you will soon see why machine learning is a key component, literally and figuratively. So here's the model. Well, first of all, it's like some of you might have seen this popular Ikigai Venn diagram before. Well, first of all, it's not Ikigai, not really. But I couldn't find any picture that doesn't have that Ikigai in the middle. Ikigai is something different, and I won't get into that. But I think this diagram itself is very interesting. Before it was merged with the concept of Ikigai. It was the Venn diagram of purpose. In fact, if I'm asked to put something in the middle, I'd put flow state instead of Ikigai. But anyways, I think it's a good starting point for researching a career path. It's saying that we need to align our 4 elements, essentially. What you love, what the world needs, what you can be paid for, and what you are good at. And if you put them in a Venn diagram, different intersections would correspond to different feelings and states in life. For example, if you have all 3 in your career, but you are missing what you love, you'd end up with comfort, but feelings of emptiness. Or if you miss what the world needs, you'd feel satisfied, but also have feelings of uselessness. But I think this is actually far away from being an accurate model. Why? Because there are obvious things missing. So, well, those 4 elements are essentially 4 basic needs we would like our career to help us satisfy. But human is complicated. We have a lot of other needs too. For example, I myself have a strong need for creativity and curiosity, and they're not captured here at all. Well, I could have all 4 aligned, but if creativity is missing, I'd still feel feelings of emptiness. You might argue that, well, isn't that just what you love? But I think it's not, because there are things I'd love to do which doesn't have to be original and creative, yet I still love it, like badminton. If you train professionally, you know basically it's like chess. And if anything, or if there's something you think you invented, there's either a better move to do it, like better way to do it, or it was already invented before. Well, a more extreme example is that, well, I just love running, right? Just keep running, and there's no creativity in that. But I used to run around king circles before the pandemic and lose track of time, and there's like zero creativity there, but I still love doing it. So I think it's not the same thing. You can't summarize that with just what you love. For other people, they might have other needs too, like how I know, like for some people, athletics is like the meaning of their lives, and those are just some examples off of my head. There must be a lot more. So I guess the question is, how do you discover those elements in your life? Like given the constraint that you can't just take every major and you gotta build a resume when you graduate, like you can't just explore aimlessly, right? You only have limited time, and you have to think about how do you put up a coherent story when you graduate. So this is where machine learning can literally help. There's this vast universe of machine learning and AI, and if you think about it, it's like almost anything is related to AI. So why not build a foundation in AI and then explore outwards and inwards at the same time and have a coherent theme called AI? For me, I already mentioned that the more I learn about AI, the more I realize how much we're kind of taking things for granted. Basically, our everyday daily human behavior is pure magic. You see this when you see this clearly when you try to mechanize and reproduce them with algorithms. And it was this feeling that led me to discover more and more of myself. And this is why AI is the theme of my research so far, and I believe it could also help you, even if you might be very different from me, because the space AI could cover is just so big and so vast. So here's an incomplete list off the top of my head. Without AI as a central theme, your research might be just too scattered around, segmented and fractured, lacking a theme. And realistically speaking, it might give you a hard time applying to grasp with, and also more importantly, you might not get, you might get lost yourself and feel frustrated when you just, when your life is like lacking a coherent story where everything's kind of scattered around. Yeah. So now let's say you've explored around and have a rough idea of what your needs are. How do we find the direction to maximize meaning? So I think meaning is a feeling. Essentially, we need to maximize positive feeling. It'd be very helpful if we know the weighting of different needs, because we probably won't be able to find something that satisfies every single need right from the beginning. So we'd have to make proper trade-offs. There's another thing missing from the Venn diagram, essentially, if you think about the trade-off, because well, the four circles are equal in size. And from the information visualization point of view, this implies they're equally weighted, which is definitely not true. So the most naive model for finding the right ways is like linear regression model. After Roger's talk, you probably already have a sense of what it is. It's basically like a one-layer neural network with linear activation. And you can solve for the optimal weights either analytically or with gradient descent. Well, in our case, the y variable is how much meaning we feel, and x is a vector with each element corresponds to a need. So each activity is, and each activity is a data point. But the problem is the weighting of different needs static and independent of how much each need is being met? Well, I don't think it is, because here's the famous Maslow's hierarchy of needs, where it's saying that human needs have priorities. We're prioritizing needs at a lower level when it's not satisfied, and we move up one by one. And we'll only focus on higher needs once the lower needs are satisfied. So essentially, there is a different set of weights at each level. And furthermore, at different stages of life, the weights of needs are also different. And this is one topic studied by the field of developmental psychology. So for example, there's this theory by Eric Hansen on stages of psychosocial development. I won't get into details, but basically the point here is that the weighting of our needs are also changing with time. And it dependent on and also dependent on what needs are being already met. So how do we take those two factors into account in our model? So you guessed it. Now you can tell me what deep learning is. We didn't need a deep neural net for such a complicated task, and we can train it end to end. So here's the algorithm. We can do deep learning on the self. Here we are treating the self as a big black boxed neural net, and as in my opinion, this is exactly what it is actually. Humans are complicated. I recall earlier I said, oh, what happened? Recall earlier I said how we never get the ground truth of the model of the self. Well, and we can only approximate it as accurately as possible. So the essential question here is that how we can do it concretely, and this is where deep learning can help figuratively. I haven't tried writing and running the actual code to learn this model, just a disclaimer, but I think this is a heuristic that we can use mentally to research effectively. So here's the algorithm. It's a two-stage algorithm. And the first stage is learning the model. Here we sample an activity and we feel how this activity is satisfying our different needs. And we treat them as the input vector X. And then we evaluate how much meaning we feel from this activity and treat it as the like how we feel as the output Y. With X and Y, we can approximate the mental model of the self by training it with gradient-based optimization algorithms. It's basically, two steps. We need to first get a gradient, and then we just follow the gradient, which Roger already talked about in his talk. And the second stage is based on this learned model. So now we maximize Y. The meaning is essentially a feeling. So if you're familiar with phenomenology and consciousness, or just familiar with psychology and cognitive science in general, you see that we can only experience the world indirectly through our brain's interpretation of events and information. So this feeling of meaning is no exception. it is very personal. So you gotta feel it and get some gradient and then follow it. The second stage is actually how you can sample activity in the first stage. Once you follow the gradient and arrive at a good X, like a good activity, or you can find the activity that is the nearest neighbor to this point X, and then use that to repeat stage 1 to further train a mental model of the self. So as you get deeper into machine learning, you'll see like algorithms that share similar tastes, like deep dream, wake sleep, or activation maximization. So yeah, but you can kind of do that on yourself. And I think the hardest step here is getting the gradient, because we don't have a differentiable simulation of our environment. We can't really take the analytical gradients, but we can estimate the gradients, like how it's done in reinforcement learning, like the most basic reinforced gradient estimator. So like all other estimators, we'd want our estimator to be consistent and unbiased. We'd want them to and also we'd want them to be sample efficient. So basically, being consistent and unbiased will give us like an estimator that as we get more samples, on average, our gradient estimate will be very close to the true gradient. Well, technically, it should be exactly the true gradient. And sample efficiency is that we basically want to be efficient. Like we want to get the most out of limited data, because it takes a lot of time and energy to explore around. And just like in the cafeteria analogy, we have like fixed sized stomach, so like all those resources are fixed. So yeah, so gradient estimation is a very hard problem, both in deep learning, and it's also a hard problem in real life if you run this algorithm on yourself. So in real life, our gradient estimates are very noisy and biased, and most of the times are just completely ignored, because most people, I guess, like most people just follow their heart, right? So you might ask, why making everything so complicated when you can just go with your heart, go with your gut feelings? Should we follow the gradient or follow the heart? So I think both are important, and neither alone is sufficient. Meaning is a feeling. So to get the gradient, of course, you need to feel with all your heart. But at the same time, I think that alone is not enough. It is well known where Earthlings are like full of cognitive bias. If you want to read more about that, you can check out Thinking Fast and Slow. Logical reasoning is a powerful tool to optimize for a particular goal. It doesn't matter what the goal is. Like it could be a very emotional goal, and counterintuitively, a logical person might even achieve this goal better than like an emotional person, like Spock. Like if you watch Star Trek, and the heart can basically tell you what it means, and then you would want some help from the. Well, it can help you to set the goal, but then afterwards, it could use a lot of help from the brain to actually achieve the goal through logic. So in 2017, I was intrigued by the divide between emotion and logic. So much so that UTMIST logo almost went with something similar to the thing on the left there. But then, because when the logo is small, it's very hard to see something like that. So we eventually went with the current logo. But now looking at this again, I had a better interpretation. Well, instead of like focusing on the divide, like between the logic and emotion, we can instead appreciate appreciate the togetherness, right? They're forming a single brain. So instead of looking at the divide, we can appreciate the togetherness. I think that's another interpretation. And I think that's where we can find the wise mind. So I'll get back to this later. Also, Jordan Peterson talked about this in his in his language, and also lessons from Carl Jung. He said, as Jung pointed out quite rightly, that people don't really think, but the thoughts just appear to them, and you can take the thoughts that appear to you, and then you subject to criticism, elaboration, and so on, instead of just assuming that they're true right off the bat. But people don't do that. Something pops into their head, and they just assume it's true. So that's, I guess, the problems for that's the cause of a lot of problems. So what he said there is, I think, the root of many fundamental problems that lead to suffering and basically make research impossible. So it's articulated in many psychology books, just to name a few here. Essentially, when we're don't going after the truth, we get the wrong gradient, and there's no guarantee where you will end up with that. It's basically just random. And let me remind you of what Carl Jung said again, until you make the unconscious conscious, it will control your life and you'll call it fate. I think here the culprit is what's under the water, the unconscious. Well, in the happiness hypothesis book, this is also symbolized as the elephant under the water. So then you might ask, why would our brains ever want to be unconscious? Now that we know that it's like, well, from the I talk about how self-knowledge is not free, right? So it's actually the default state, but why, right? I think this is a rabbit hole that goes very deep. So Socrates said, to know thyself is the beginning of wisdom. I think it's only the beginning of, I think it's not only the beginning of wisdom, it's also the beginning of a lot of things. Once you know yourself, you'll realize what you've been calling fate is actually just your unconscious self. And now that you can realize you actually have full control over that, so then there will be no excuse for any of your wrongdoing. You're empowered, but also burdened with responsibility. Now you need to take extreme ownership of yourself. To me, that's like a huge part of the meaning of life, but I observed that for many, it's really scary and it's like a huge burden. And you've also just get to meet your shadow, the dark side of the self. It's not like it's not there when you're not looking. It's always there, but it's just being hidden under the water and secretly manipulating you, and you thought that was fate. Well, now that you've met this terrifying being, it is your chance to make friend with it and make peace with it. In reality, though, most people are terrified at this, whether they know it or not. Otherwise, we would be in a world free of conflicts and mental disorders. This is the point inside of humanity, and don't get me wrong, it's perfectly human to be like that. But it is indeed one of the biggest barriers for research and from getting good gradients. And I believe we can do something about it.
Hi, Sheldon. Just a friendly reminder, you have 5 minutes.
Okay. I think if that's the case, I won't be able to get through the talk. Let me see where I can trim. So I'll just go and see where, how far I can get. So the first thing we can do about it is to recognize the nature of it without judging. So in the book, The People of the Lie, Scott Peck focused on the narcissistic characteristics and how it is a defensive phenomenon. He also pointed out that in some sense, we're all narcissistic to some degree, because it is only human to feel discomfort when you take a good look at your flaws and weaknesses. So when this gets pathological, one would be controlled by what he called the human evil. And the fun fact from the book, evil is basically lie spelled backwards. So in fact, the unconscious can stay hidden, and it's not merely a coincidence. The self can never Okay, I think I need to finish in 1 minute, so let me think. Let me just maybe skip to the end. Yeah, there's lots of content, but to skip to the end. Yeah, so to get more accurate gradients, I think we need to pause when we are kind of being overwhelmed by fear, and this is set in radical acceptance. And until we stop our mental business, stop our endless activities, we have no way of knowing our actual experience and in our language. And in our language, the gradients. So this is also why people, when they're in the state of kind of half conscious, they distract themselves with all sorts of clever ways to keep themselves busy. But they pay a very heavy price for it. And the price is basically becoming numb and secretly controlled by unconscious. And Also, it would help if you kind of articulate exactly what you're feeling, and that's basically from the power of articulation. So that would basically help us to uncover what's unconscious. And also, there's this paradox of fear. Once you kind of you're facing it, it's gone. And this is like a theme in a lot of movies, like if you horror movie, if you watch it, it's called It. Like once you face the fear, it's basically gone. It's kind of, yeah. So I think if you're, instead of if you're not facing it, it will get pretty strong and control you. So basically, I think the right way to go is that you should accept that fear is part of you and say to it, befriend it, say to it that it belongs, and basically make it a friend instead of a foe. So I'll skip this part. Yeah, so once you're kind of okay with fear, I think you already completed the 2 steps here that with self-awareness and self-acceptance. And there will be other barriers too in your research, basically like societal pressure and stuff. I think that basically that's something you can't really control because it's like external environments. And the way to get around that is through self-compassion and self-love, which is the second half of this mindfulness approach. And those are like some pointers to books that kind of articulate this point. And yeah, so yeah, I think it's impossible to finish them in 1 minute, so I'll just skip over them and let's see. Yeah, and once you kind of practice those 4 states, self-awareness, self-acceptance, self-compassion, and self-love, you will basically be able to slowly turn those states into traits. Like basically every time when you're encountered with stochasticity and external chaos from the environment, it will start another loop, another circle. And once you kind of repeat this circle enough, those states will become traits corresponding here, like emotional intelligence, inner peace, resilience, and anti-fragility. And then it will become, then I think you will slowly uncover your true self, which is like the objective of the research. And that will be your wise mind. Yeah, and once you have that, I think you're equipped with the traits that to handle like a lot of uncertainties, and also like if pandemic is kind of like a impact on all of us, but I think it's possible to have post-traumatic growth, and there's like psychological experiments in that, which I don't have time to get into today. But I think we can take the opportunity to build character by escape the trance, which is the half-conscious state induced by uncertainties of fear, and turning those positive states into traits to achieve anti-fragility. And I think we should be grateful in spite of our suffering, as pointed out in Beyond Order, the book. Yeah, and that was it. Hopefully I'm not over time by too much. So I want to end my talk with an invitation to you, the eager young minds of tomorrow, an invitation to boldly go to find some meaning and to clear some mist. So we welcome you at UTMIST, and thank you for listening.
Thank you, Sheldon. That's an amazing talk. And thanks for sharing the many ideas on research. And there are a lot of good books. So now I will share my screen again. Next, I'd like to introduce you to the organizing team of UTMIST this year. They will be the ones ensuring that everyone involved in our projects and events get good experience. And we'll talk about how you can join us toward the end of the presentation. So before I introduce our VP, let's cover the structure of the organizing team at UTMIST. So working at UTMIST is all about gaining meaningful skills, connections, and there are essentially three components: project, events, and content. The infrastructure team develop new features to our website. Academic and research, as well as engineering department, work on implementing machine learning projects. They, as well as the industry relations team, also work on developing different events. Marketing focuses on finding ways to grow our organization. Technical writer focus on discovering, understanding, and informing others about exciting things in machine learning. University relations help us stay connected with other student organizations. And last but not least, we have internal affairs department that ensure the smooth running of the club and help us stay connected with U of T. Now I will let each VP talk about their own department.
Hey guys, I'm Theo. I hope you guys have all been enjoying the AGM so far. I'm the VP Academics for this year. So I kind of want to share the academic department. So our main focus is to promote machine learning research and education. So you guys will find that our events center around this theme. First off, we have 2 academic projects this year, which focus on the exploration of machine learning concepts, as well as some paper reproduction. And second, we also have a suite of academic events for students looking to learn more about machine learning. So first off, we have paper reading groups, which will highlight impactful works throughout machine learning history, and also learn about a lot of emerging works at the forefront of the field. We also have a study group, which will be the Introduction to Deep Learning course offered by Coursera. And students will find the materials really interesting and relevant for machine learning, and has a lot of programming assignments to brush up skills. We'll also have a series of 2 UTMIST talks, which will be from researchers to discuss their work and showcase different aspects of machine learning. And overall, to support these events, we have a team of mentors to provide direct assistance for project-related questions, as well as to monitor Discord and answer other machine learning-related questions. So if any of this sounds interesting and you want to get involved, we have positions for project developers that are currently open, as well as mentors if you have more machine learning-related experience. So now I'll pass it over to Arsh.
Thanks, Theo. Hey, everyone. I'm Arsh, and I'm the VP Engineering for the 2021-2022 academic year. I hope you're all having a great start to the weekend. The engineering department plays a huge role in the activities that UTMIST does on a yearly basis. The core focus of the engineering department are our applied projects, where many different student-led project teams focus on building practical machine learning applications that aim to solve real-world problems. Furthermore, many of the project teams are looking for project developers to help execute their projects over the next 6 months. If you're interested, please check out the posted projects and developer postings on our website and apply to teams that you would like to. These projects will also be presented at our brand new end-of-year MIST conference in March 2022. We're also working with the Entrepreneurship Hatchery, who will be providing interviews to the project teams to help scale their projects to a completely new level. As a part of working with these project teams, accepted developers will also have a chance to collaborate with the many mentors and resources that UTMIST has. Developers can use these interactions to elevate their machine learning knowledge and capabilities further than ever before. Altogether, it's a pleasure to talk to you all about the incredible engineering work that UTMIST is doing. And if you're interested in working with our machine learning projects, please check out our website for more information on how you can sign up. Thanks, and I'll pass it over to Kathy.
Okay, thanks, Arsh. Hi, everyone. I am Kathy, and I'm this year's VP University Relations for UTMIST. Here are 2 things our department focuses on: outreach and club fairs. So for outreach, we connect with the student body and the school faculties. We build partnerships with student organizations on our marketing promotions, as well as events such as workshops and conferences. We also collaborate with school organizations and faculties on workshops, conferences, and hackathons. Through these partnerships, we hope to provide more resources and opportunities to our members. Some of you might have already talked to Vicky, Tad, Anna, and I during several online club fairs. The UR department is in charge of introducing UTMIST to more U of T students through online and in-person club fairs. So we believe that UTMIST has something for everyone. So through club fairs, we hope to meet many talented minds that are interested in machine learning and would like to build this fascinating community with us. So if you see me on the club here, come and say hi. And also if you belong to a club on campus and you would like to collaborate with UTMIST, come talk to me. We're open to any form of collaborations. And that's all about our department. Thank you. And we'll move on to the industry relations.
Thanks, Kathy. So hi guys, my name is Kavya. I'm this year's VP of Industry Relations for UTMIST. And a little bit about the IR department. We're basically responsible for 3 main branches of events that we host throughout the year. First off, we have our university events. So these are essentially any ML-focused events that we hold in collaboration with other clubs or other professors or graduate students who are interested in sharing their research and their work in the field. This is our chance to give back to the U of T community by working alongside the different faculty and, hosting fun and educational events. We also have here our industry events. So these include things like speaker panels, conferences, workshops, tech talks, and a lot more than that. And these are when we collaborate with industry professionals outside of U of T, and we let them share their work and their knowledge with U of T students. These are especially cool because industry events give you the opportunity to network with people outside of school. So you get to, get the opportunity to meet interesting folks and learn about interesting topics. And last but not least, we also offer a division of mentorship. So this includes providing the U of T community with different resources that help propel you into the ML field. So whether that be guidance, support, advice, important industry insights, it's all to make you feel more prepared as you enter the industry. All in all, we're just working with the rest of the different departments to provide you guys with the best resources, the best events, and the best opportunities. So make sure you guys keep an eye out on our website for our new and upcoming events. They're going to be great, and you'll get to learn a lot of different things. So yeah, I look forward to seeing you all there. I'll pass it on to Anna to talk about our IA department.
Thanks, Kavya. Hello, this is Anna. I am the VP of Internal Affairs this year for UTMIST. And I'm the person who helps with the internal administrative work at UTMIST. So I'm responsible for our finance, our maintaining our club status, and facilitating the CCR recognition to make sure that you can find us at UTSU, ASO, and ULife. So I'm the go-to person for reimbursement if you have to purchase anything for our club, and if you wish to get your time recognized with us at the CCR as an executive member, project developer, associate, etc. That's where you will come to me. And that's about it from the IA department. Enjoy the rest of the talk. I will pass it to Afnan.
Thanks, Anna. Hi, everyone. I'm Afnan. I go by the pronoun she, her, and I will be the VP marketing for UTMIST this year. A little glimpse into the marketing department. We are responsible for conducting data-driven market research, developing effective marketing campaigns, and serve as a creative liaison for UTMIST's public events and workshops. As you can see, the team focuses on 3 areas. The first one being the content creation. The content creators, who are essentially the graphic designers, photographers, and videographers, will be the creative minds behind the promotion of UTMIST's upcoming initiatives. They would also be creating graphics and videos by keeping UTMIST's values and brand alignments in mind. The marketing department is also responsible for generating cloud and increasing student engagement for UTMIST through outreach. This entails building and maintaining inter-club partnerships, social media advertisements, and collaboration. This leads us to the last area, which is the social media management. Currently, our main marketing channels are Facebook, Instagram, Discord, and LinkedIn. Now, if you have passion for creative design and looking to get involved, we may have the perfect opportunity for you. Currently, we have few positions open at the marketing department. We will be hiring 2 more graphic designers, 2 more outreach coordinators, and 1 assistant to VP marketing. You can find more information about the roles and how to apply on our website. I will also share the application link in the chat. Please reach out to me through Discord if you have any questions regarding the portfolio or any of the roles under the marketing domain. And now I will pass it over to Richard to introduce his department, technical writing.
So thank you, Afnan. Nice to meet you all. This is Richard. If you've been to our events last year, I'm pretty sure you saw my face a lot. So this year, I'm one of the people responsible for covering interesting machine learning news, along with a talented crew, which includes Natalie, Fiza, Grace, Elena, and Charles. Our main task is to discover, understand, and inform others about exciting news in machine learning. We present summaries of academic papers and industry news, along with some UTMIST content and helpful resources. We meet on a monthly basis to discuss our interesting findings. We produce Medium blogs, email newsletters, and YouTube videos. We provide support also for our marketing department in reading and translating their works. To me, reading and writing about machine learning is one of the best ways to learn machine learning. It's also very rewarding to have readers getting inspired by our works. Please support our works and consider subscribing to our newsletters, YouTube channel, and Medium. Thanks. Now I'll pass it on to Hugo, our VP Infrastructure.
Hi, everyone. Thank you, Richard.
So the infrastructure team works on the infrastructure that allows the team to be able to work on ML projects and share their findings. While they don't work on any ML projects, they do apply software engineering skills in order to facilitate the smooth running of the club. There are three things that the infrastructure team focuses on. First one is providing computer resources. So that includes providing GPU compute power for projects to run. Second one is maintaining the club website. So we have a beautiful website. Thank you, Hugo and team. The third one is moderating the Discord server. So if you haven't joined our Discord server, please click on the link in the chat. And now we'll talk about how you can participate. So you can join our Discord newsletter event. You can join our study group. We'll go through a course on Coursera. The third one, you can join our paper reading group. And you can become a project developer. All of the projects can be found on our website. And last but not least, you can join our marketing team. All the postings are on our website as well. And if you have any questions, please reach out to Afnan. Thank you all for being here. Yeah, I guess I will stay a little longer if you guys have any questions.